Hey peeps, hope you are doing well and I believe that you have seen the previous videos. So in this lecture we will try to discuss about the temperature effects in conductors and semiconductors in their properties. So by properties I mean how the band diagrams change, right? So in the previous videos we have seen that in the case of a conductor we have the valence band and the conduction band overlapping with each other, right? And we have also seen that the valence band is filled with electrons, and since the valence band and conduction band overlaps, the conduction band is partially filled with electrons. So valence band is completely filled with electrons. The conduction band is partially filled with electrons. Now, since in the conduction band there are some electrons, now this is a scenario at temperature T is equal to 0 and I'm talking about conductors. So at T is equal to 0 Kelvin, okay. So even at T is equal to 0 Kelvin, there are some free electrons present. So since free electrons are present in the conduction band, these electrons could help in the formation of some current even at 0 degree Kelvin. So the property of a conductor is that even at 0 Kelvin, a conductor can conduct because there are free electrons present in the conduction band even at 0 degree Kelvin, right? Okay. Now, when I talk about a semiconductor, okay, semiconductor, that's not the case, right? Because definitely the valence band and conduction band have some kind of a forbidden energy gap, which is called the band gap, 1.1 electron volt in the case of silicon, right? So definitely the valence band is filled with electrons, that's what we have seen, and the conduction band is completely empty, right? So I'll write valence band completely filled and conduction band completely empty. So definitely this is the case at T is equal to 0 Kelvin again. So definitely since there are no electrons in my conduction band, definitely it's not able to conduct. So it behaves like a insulator. Okay. So a semiconductor behaves like an insulator at 0 degree Kelvin. Right. Now what happens when I try to increase my temperature? Now when I try to increase temperature, as you all know, electrons will start to gain energy. And definitely some of the electrons will start to jump from the valence band to the conduction band by breaking the electrons, right? So what I mean to say is that in the case of conductor it's quite very simple, okay. So more electrons will come into the conduction band. So what happens here is that an electron will jump from my valence band to the conduction band. I'll depict that once again. So let's say I'm talking about this electron here, right? So this is gonna jump from this point to this point when I try to increase the temperature. Definitely this electron will reach and this will lead to a vacancy. Definitely it will lead to a vacancy, right? So you have electrons and a vacancy of electron which is called the hole, right? But this hole is not very significant in the case of conductors. Why? Because even at 0 degree Kelvin, there were so many electrons, right? There were so many electrons which could result in current. Now, even if I try to increase temperature, what happens here is it's basically these electrons gonna jump, but that is not gonna change any concentration here. Why? It's because even at 0 degree Kelvin, the concentration of electrons here, okay, even at 0 degree Kelvin, the concentration of electrons in the conduction band is very high. Okay, the concentration is very high, even at 0 degree Kelvin. So, even if I try to increase temperature, it's not gonna change so much. Okay, so I can say that in the case of conductor, this is a very important point. The free electron concentration, the free electron concentration is independent of temperature. So it's just like even if one electron comes up, that is not going to change. Even if one electron loses, not going to change. It's just like nothing is happening. Okay, it's just like nothing is happening. Why? Because it's independent of temperature. So even if there was no temperature, then definitely no electron excitation would have taken place. That scenario is equivalent to that of applying a temperature, right? So what I mean to say is that the free electron concentration is completely independent of temperature. So if that is the scenario, definitely a hole doesn't matter. Doesn't matter. Or an electron even doesn't matter. Okay. An extra electron. I'll write extra electron doesn't matter. So that's a scenario. Fine. So definitely the free electron concentration. So definitely the conduction in conduction band of a conductor is actually dominated completely by the free electron concentration at 0 degree Kelvin. Fine. So yeah, so the conductivity is only affected by, so conductivity is only affected by free electron concentration. Okay, free electron concentration at 0 Kelvin. But in the case of a semiconductor, that's not the scenario. Why? Because every electron comes here, that can lead to a formation of a current. So definitely that's going to matter. So what happens in the case of a semiconductor? Let's see. So at T, let's say is equal to 300 Kelvin, I have increased my temperature to room temperature. So what happens here is that some covalent bonds are going to break. Right. So let's say that I'm having silicon. Right. So you have silicon atoms arranged. Right. So definitely you have a lot of silicon atoms arranged like this. So let's say these are my electrons. Right. So when I apply temperature, some of these covalent bonds, okay, some of these covalent bonds are gonna break. So what happens when a covalent bond breaks? This electron excites itself to the conduction band. So this electron goes to the conduction band and this leads to a vacancy. So what happens here is something like this. So let me draw my conduction band here and let me draw my valence band here. So At 0 degree Kelvin, you have a lot of electrons. Okay, and when I increase my temperature, what happens? These electrons will start to excite. So let's say this electron excites somewhere here. So one electron comes here, and this electron gets lost, right? So that leads to a vacancy. Now, in the case of semiconductor, definitely both these electrons or holes are important because this electron can move around in the conduction band, and definitely a hole can move around in the valence band, right? A hole can move in the valence band. So what does that mean? This electron can jump in here, so that means that the hole, okay, this electron can jump inside the hole, so this electron goes here and this hole comes here. How? I'll demonstrate it once again. So let's say this is an electron. So what happens when this electron occupies the hole? This electron comes here, but now here you have a vacancy. So you have this hole slightly moving like this. Correct. So definitely, uh, as one electron occupies the hole, now the hole comes here, right? Now the next electron, let's say there was some electron here. Now this electron can occupy this hole, and this hole moves here. Correct. So definitely you can have hole motion, and that's quite good because holes try to be at the lower energy level, but electrons try to be at the higher energy levels, right? So you have electron motion and hole motion, and both these motions are significant. In the case of conductors, that was not at all significant because you have tremendous amount of electrons at 0 degree Kelvin, and thus your concentration is independent on temperature. But here it's not. So as your temperature increases, more and more electrons come, and more your conductivity is gonna become. So the electron and hole both are significant. That's the main key here. True. So one main point which I would like to make here is that electron and holes get generated, right? So this generation is called an electron hole pair generation. This always happens in pairs, right? This always happens in pairs, and this depends. Okay, the main point is this generation of electrons and holes electrons and holes depend only on temperature, or I can say depend heavily on temperature. Depend heavily on temperature. I can, that would be a better suitable word. Depend heavily on temperature. Now, similar to this process, there is something else which also happens inside a semiconductor. That's something that makes semiconductor so special. So that is, once you have sufficient amount of electrons in the conduction band, yeah, once you have sufficient number of electrons in the conduction band, let's say you have 3 electrons, right? Now there is also one more process, which is, if there are 3 electrons, definitely there are 3 holes also, right? So let's say these are my 3 holes. Now definitely there is one more process, which is the recombination process. Okay, the recombination. Now what is recombination? Recombination is the process where an electron in the conduction band goes down and occupies a hole in the valence band, right? Now, why does this happen? This recombination happens and is heavily dependent on, okay, recombination happens and heavily depend on the concentration ratio. The concentration of carriers in valence band and conduction band, not on temperature. So this is a key point. So what is a key point? Yeah, the electron pair generation depends heavily on temperature, but the recombination does not depend upon temperature, but it depends upon the concentration of carriers in the valence band and conduction band. Now, what does that mean? So, as you know, that due to temperature, you have this electrons in the valence band. I mean, these electrons exciting to the conduction band, right? So, you have electron hole pair generation due to temperature. Now, as you can see, that as this process happens, the concentration of electrons here is decreasing because these electrons are getting excited, right? While the concentration of holes here is increasing, right? Now, if I think of the same scenario in the other way around, I can say that initially there are a huge number of holes inside my conduction band, which means there are a lot of electron vacancies in the conduction band. Okay, or there is electrons absent in the conduction band. Right, all actually mean the same because there are a huge number of holes in the conduction band, which is equivalent to saying that there is a huge number of electron vacancies. Right, so since the whole concentration is high here, the whole concentration is low here. Similarly, the electron concentration is high here in the valence band and electron concentration is low in the conduction band. There is definitely a concentration difference, right? So, depending upon the concentration difference, it's not actually difference, but the concentration ratio in the valence band and conduction band, there is recombination. So, both these processes of the electron hole pair generation and recombination happen at the same time. So there is one more thing which I would like to emphasize here, which is the electron hole pair generation and electron hole pair recombination is governed by two ratios, by two rate, alpha and alpha. Okay, alpha G and alpha R. So alpha G is the rate of electron hole pair generation, and definitely this rate depends only on temperature and not on concentration. Dependent. Okay, and you have alpha R, which is a recombination rate, right, and depends only on concentrations. Now we will see more about these in the next video. So stay tuned and learn your concepts well. All the best.